Welcome back, folks. We are going to get started with a review of the rules we have already covered for AC circuits. Then we're going to show the voltage divider and current divider for AC circuits. We may as well start at the beginning with Ohm's law. We can subdivide that into the DC side of the house and the AC side of the house. Early in class, we learned that a voltage is a current by a resistance. That Ohm's law equation has transformed into a voltage vector is a current vector by a impedance. We learned about Kirchhoff's voltage law, which told us the summation of the voltages on a closed loop was equal to 0. That equation still holds. Now we recognize it as the summation of the voltage vectors in a closed loop is equal to 0. Could look at it this way. We could talk about E1 plus E2 plus any number of voltages is equal to 0. Or over here, voltage vector 1 plus voltage vector 2 plus any number of voltage vectors add up to 0. Kirchhoff's current law tells us that the summation of the current is equal to 0. On the AC side of the house, the summation of the current vectors is equal to 0. And we can write that another way where we say the goes intos has got to equal the goes outas. Likewise over here, the summation of the current vectors leading into a node is equal to the summation of the current vectors leaving that node. We explored series circuits. There we said the total series resistance was equal to the summation of the resistors. That same thought holds for AC circuits. Let this be R1, L1, and C1. In this example, our total impedance is the sum of the individual impedances. Do be careful, as each of these must have units of ohms. Inductors become J times the inductive reactance, and capacitors become negative J by the capacitive reactance. Recall that the inductive reactance is 2 pi FL, and the capacitive reactance is 1 over 2 pi FC. Parallel circuits. One over the total resistance is equal to 1 over R1 plus 1 over R2 plus as many resistors as you have in parallel. On the AC side of the house, we have to be careful to express our inductors and capacitors in terms of their impedance. So an inductor would be JXL, and a capacitor would be negative JXC. And now we can perform the calculation. So 1 over the total impedance is equal to 1 over the first impedance plus 1 over the second impedance plus, and we continue that pattern for as many impedances as we have in parallel. We mentioned this before, but it bears repeating. This piece is reactance. You'll notice there are no imaginary components associated with reactance. Reactance is a scalar. What we need to do is calculate impedance. And the impedance requires use of the real imaginary plane. Our inductors are here, our resistors are on the real axis, and our capacitors are negative creatures. We would describe an inductor as J XL, and we would describe a capacitor as negative JXC, where this is the inductive reactance and this is the capacitive reactance. As a side note, you've seen J or I in other math classes, and we describe that as the square root of -1. Fair enough, that's what it is. That is the definition. However, when we think about it in terms of our electronics, I would encourage you to think of J as a rotation off the real axis. So J is actually a 90-degree rotation. And you can see that on your calculator. If you just enter J all by itself, so 1J, and you shift complex and then go to polar form, you'll see that it's 1 at a phase angle of 90 degrees. So J is actually just a rotation of 90 degrees. It gets you from the real to the completely imaginary. Likewise, if you had negative J, and you looked at that in polar form, there it is. Negative J is just a rotation in this direction. That might be a good way to remember what J actually means. For some real fun, go ahead and square J. So parentheses, J, and then square it. What do you think you're going to get? If 1J gets you to 90 degrees, it might make sense that 2Js would get you 180 degrees. And sure enough, there's -1. If we put that into polar form, 1 at 180 degrees. You could continue that game. If you cube J, you get to 270 degrees. And if you take it to the 4th power, you get back to where you started at 360-degree rotation. Something to keep in mind. And the other thing, just remember that capacitors are negative creatures, and you'll be all right. Remember, reactance is a scalar. It's a magnitude with no direction. Impedance is a vector. It has both magnitude and direction. Which is why we talk about the voltage vector. We talk about the current vector. And we talk about the impedance. And impedance has both magnitude and direction. In the near future, we can look forward to talking about complex power, which is also a vector. Moving on, let's talk about the voltage divider. Given a series circuit, the voltage of interest is equal to the impedance of interest over the total series impedance, all multiplied by the source vector. For example, if you wanted to know the voltage as measured across impedance 2, you would calculate that as the voltage on impedance 2 is equal to impedance 2 over, in this particular case, impedance 1 plus impedance 2 by the source vector. We'll go over an example or two in a couple minutes, but before we do, I wanted to introduce the current divider. In this circuit, we have our source current, which is expressed in terms of a phasor. And then we have 3 impedances that are in parallel. We also have this piece here, which I'm going to call the impedance of the grade robbing trap. Please do not fall into it. Know that this has nothing to do with the current divider because this is not part of the total parallel impedance. The current divider is the same for AC as it was for DC. We have the current of interest is equal to the total impedance over the impedance of interest multiplied by the source current. Never forget that this T is the total parallel impedance. This grade robbing trap is not part of the total parallel impedance. In this particular example, these three impedances form the total parallel impedance. Those are the two things I really wanted to talk about today, the current divider and the voltage divider. And now we'll go over a few examples to show how each of these are applied. In this example, I'm going to use the word load to refer to this part of the circuit, and I'm going to use the word line to refer to this part of the circuit. So we could talk about the voltage drop across the line, and we could talk about the voltage drop across the load. A voltmeter in this position measures the load voltage, and a voltmeter in this position measures the line voltage, which in this case includes both the resistance and the inductance. Your opening move in this problem is to calculate the inductor's impedance. The reactance of the inductor is 2 pi FL, in this case 2 pi by 60 hertz, and 0.005. 2 pi times 60 times 0.005. So that's about 1.88 ohms. And I'm going to move that directly upstairs here. I'm going to say that's J 1.88. So now we have units of ohms, ohms, and ohms, and we can move forward with our calculations. Using the voltage divider, we can calculate the load voltage as the impedance of interest, which in this case is 20, over the total impedance of the circuit. Since this is a series circuit, that would be 2 plus J 1.9 plus 20, and all of that is multiplied by the source voltage. Let's go ahead and collect all of our terms here. So that's 20 over 22 plus J 1.9 by 120. 20 divided by 22 plus 1.9J close equals by 120. And we're going to put that into the polar form because that's what your voltmeter is going to read, which gives us 109 volts at a phase angle of negative 4.93 degrees. The line voltage is calculated as the impedance of interest, which is these two together. So that's 2 plus 1.9J over 22 plus J 1.9 multiplied by the source. So that's parenthesis 2 plus 1.9J close paren divided by parenthesis 22 plus 1.9J close equals by 120, and then we shift back into polar form. So that's about 15 volts at a phase angle of 39 degrees. If we put these two together and talk about Kirchhoff's voltage law, we should see that the sum is equal to the source voltage. So we can say 15 at a phase angle of 39 plus 109 at a phase angle of negative 4.9 should equal about 120 volts. And we come out pretty close here, about 120 in some very small angle. So it looks like Kirchhoff's voltage law is satisfied. If we were to show that using vectors, there's the real, there's the imaginary, we would talk about the voltage source as 120 volts at a phase angle of 0 degrees. We show the load voltage, greatly exaggerated, as 110 volts at a phase angle of negative 5 degrees. Finally, we show this vector here, which represents the line voltage, again, greatly exaggerated, as 15 volts at a phase angle of about 40 degrees. This graphical head-to-tail vector addition is the same thing we did here with Kirchhoff's voltage law. Let's move to another problem, slightly more complicated. As we did in our previous problems, let's agree to call this the load and this the line, which means we can talk about the voltage as measured across the load or the voltage as measured across the line. Our opening move is to calculate the impedance of the inductors and capacitors in this particular circuit. The reactance of L1 is equal to 2 pi f L. Which works out to 2 times pi times 60 times 0.0015, which is 0.565 ohms, translates to a impedance of J 0.565. The reactance of L2 is 2 pi f by 0.015, 2 times pi times 60 times 0.015, which gives us 5.65. And that is ohms. So that goes right here as an impedance of J 5.65. And finally, we can address the capacitor. So the reactance of capacitor 1 is equal to 1 over 2 pi f by 100 microfarads. So the capacitive reactance is 2 times pi times 60 times 100, 10x 10, negative 6. Now remember, I've just done this piece right here. Now I need to invert it. So we hit the equals, and then invert equals. So that works out to 26.5 ohms, which yields an impedance of negative J 26.5 ohms. At this point, I would encourage you to redraw the circuit with this piece as impedance 1 and this piece as impedance 2. Impedance 1 is relatively straightforward. That's just 0.2 plus J 0.565. The load impedance is a bit more challenging as you need to calculate the impedance of this box. So 1 over impedance of the box is equal to 1 over 5 plus 1 over j 5.65 plus 1 over negative j 26.5. So the impedance of the box is equal to 5 invert plus, did I mention you need to use the parentheses with this calculator? So make sure you put the entire piece here, 5.65j, inside the parentheses, and then invert it. Plus, again using parentheses, negative 26.5j invert equals, that takes care of this side of the equation, but don't forget this side here, which means you need to invert this. So invert, and there is our impedance. So the impedance of the box is 3.3, what is that, 3.37 plus J 2.34 ohms. Remember, we take this value and we move it over to here. So that's 3.37 plus J 2.34. Adding the source completes our redraw of the circuit. That was 277 volts, phase angle of 0 degrees. Remember, we're looking for the voltage that's measured across the load, and we're looking for the voltage that's dropped across the line. Using that voltage divider, the voltage on the line is the impedance of interest, which is this piece here, 0.2 plus J 0.565 over the total series impedance, which is the summation of these two, 3.57 plus J 2.91, and all that's multiplied by the source voltage. Using the calculator, that's 0.2 plus 0.565J divided by 3.57 plus 2.91J, close, equals, and then you multiply this by 277 and put it into polar form. So the line voltage is about 36 volts at a phase angle of 31 degrees. We then use a similar technique for the load voltage. So that's 3.37 plus J 2.34 over 3.57 plus J 2.91, all multiplied by 277. So the load voltage, 3.37 plus 2.34J divided by 3.57 plus 2.91J, close, equals, all multiplied by 277. So the load voltage is equal to 246 volts at a phase angle of, oops, we gotta put that into polar form, sorry. There, that's better. So we'll try that again. 247 volts at a phase angle of negative 4.4 degrees. Our calculator right now shows us the load voltage. If we add the line voltage, so 36 at a phase angle of 31, we should arrive back at our source voltage, which is 277. Okay, which we do, which is a statement again of Kirchhoff's voltage law. If we were to sketch these phasors on the real imaginary plane, we would have the source, 277 volts, phase angle 0 degrees. We would have the load, again, greatly exaggerated here, as 247 at a phase angle of -4. And then we would have the line right here, 36 volts at a phase angle of 31 degrees. Now that we know the voltage drops, let's go back and see if we can't calculate the current in this circuit. For example, what is the current on R1? How about L1, R2, L2, and C1? What is the current through each component? To make that a little easier, let's put these voltmeters back in, and let's record what each voltmeter is displaying. I believe this meter was 36 volts at a phase angle of 31 degrees. And this meter was 247 volts at an angle of -4.4. Let's take a look at the current on impedance 1 first. So the current on Z1 is equal to a voltage divided by an impedance. In this case, it's 36 volts at a phase angle of 31 degrees divided by 0.2 plus J 0.565. That works out to parenthesis 36 at a phase angle of 31 degrees divided by 0.2 plus 0.565 J, and polar form, please. So that's 60 amps at a phase angle of -39, I will call it -40 degrees. We can take another shot at this by calculating the current on impedance 2. And that is 247 at a phase angle of -4.4 over 3.37 plus J 2.34. Before we put that in the calculator, what do you think it'll be? Remember, we just calculated this current here going into impedance 1, and we're asking what this current here going into impedance 2 is. And I think you'll agree that this is a series circuit, so the current should be the same. So let's give that a try. Parenthesis, 247, phase angle, -4.4, divided by, parenthesis, 3.37, plus 2.34 J, and the answer is the same, 60 amps at a phase angle of -40 degrees. And that's good news. Again, it's a series circuit. You should have the same current flowing no matter which way you calculate it. Again, that calculation and that calculation are the same. So let's see, are we closer? We calculated this current here, and we calculated the current going into impedance 2. I think you'll agree that the source current is equal to the current on R1 is equal to the current on L1, which is the current we just calculated. I believe it was 60 at a phase angle of -40. So that's 60 amps at a phase angle of -40 degrees. Again, this is a series circuit for this part, so all of these will have the same current flowing through them. This piece is not a series circuit. This is a parallel circuit, so we're going to need to do a little bit more work to figure out what the current through each of those elements is. The good news is that we know what this voltage is. I believe that voltage was 247 volts at a phase angle of negative 4.4. Since we know the voltage across each element and we know the impedance of the element, we can calculate the current. Looks like we're running out of space, so we'll slide over here to do that. So the current on R2 is equal to the voltage, 247, at a phase angle of negative 4.4 divided by 5, which I believe gives us 49.5 at an angle of negative 4.4. So 247 divided by 5, which is 49.4. The current on L2 is that voltage divided by the impedance of the inductor, so negative J 5.6, 247, phase angle of negative 4.4, close, divide. That's not negative. Inductors are not negative. Let's try that again. 5.6 J. And complex 3 equals. So that is 44.1 amps at a phase angle of negative 94 degrees. And the current on the capacitor is equal to 247, phase angle negative 4.4, again a voltage, divided by an impedance, negative J 26.5. So 247 at a phase angle of negative 4.4, close, divided by negative, because it's a capacitor, 25.6 J. And polar form, please. So that's 9.3 amps at a phase angle of 85.6. And just to make sure that we haven't done something silly, let's add all of these up. And that better equals 60 amps at a negative 40 degrees. So let's see if that's true. So 49.4 at a phase angle of negative 4.4 plus 44.1 at a phase angle of negative 94 plus 9.3 at a phase angle of 85.6 and polar. Here we are. I mean, there are some rounding errors, but that's very close to our 60 amps at a phase angle of 40 degrees. Oof, that's what you call a colorful solution. It gets tricky, you see. My window isn't that large, and in order to show things, I have to kind of center around the original piece. If you're on paper, you can make things a lot neater because you have more space and you can lay out your problems logically. We did talk about current dividers, and what I'd like to do at this point is take this piece right here and redraw it, see if we can make some sense out of it. The current divider problem goes something like this. We are told that there is a current, in this case 60 amps at a phase angle of negative 40 degrees, flowing into this circuit. The circuit consists of 3 pieces that are in parallel. With this, we can go directly to calculating the current. Using the current divider, the current on R2 is the total parallel piece, which was 3.37 plus J 2.34 over 5 multiplied by the source. In this case, 60 amps at a phase angle of negative 40 degrees. So that's 3.37 plus 2.34J, close, divided by 5, multiplied by 60 at a phase angle of negative 40, which gives us 49 amps at a phase angle of negative 5 degrees. This is pretty close to our previous calculation where we had 49 amps at an angle of negative 4 degrees. The current on L1 is the total parallel impedance over J 5.6 by the source, and the current on the capacitor is the total parallel impedance over the impedance of the capacitor by the current flowing into this circuit. And I will leave it up to you to calculate these other pieces. And when you do, don't be surprised if there's rounding errors. In fact, you already saw that. We calculated current using 2 different methods, and we were close, but not exactly with the same numbers. One afterthought, let's see. I do have one afterthought for you, and then we'll call it a day. And that is mesh analysis. You might have noticed I used both what looks like a DC designation and an AC designation on these sources, and that's fairly straightforward. If you had a sinusoid signal and it was connected up in this direction, if you reversed it, it would now be like so, and those are not the same because you've had a 180-degree phase shift. So to account for that, I've drawn in the negatives and the positives. You'll be glad to know that mesh analysis is exactly the same. It's still an application of KVL. We have this current A, this current B. Walking the loop, we see negative voltage 1 plus impedance 1 by current A plus impedance 2 by current A minus impedance 2 by current B is equal to 0. In the second loop, we have impedance 2 by current B minus impedance 2 by current B plus impedance 3 by current B plus the voltage 2, all equal to 0. For this class, you will be asked to set up but not solve these loop equations.